Good morning. A couple more people coming in. Okay. So don't forget that you have a test that's currently open for you all to be taking. It's your first test. It opened up yesterday. It's all multiple choice. It's on Moodle. You have until midnight tonight to take it. Share screen. I'll show you guys. Why not? Let's just show where it is. So if we go in here, you'll see it right here. All right, test 1, chapter 2, 3, and 4. Please make sure you do that. Okay. If you don't do it, then you lose the points. We do have a grade replacement, which means if you do better on your final than one of these exams, that will swap your grade out. But you want to leave that grade replacement for like test 3 or 4. Test 1 and 2 are definitely a little bit easier, a little more accessible. Test 3 and 4 get a little bit more challenging. Okay. So open up to chapter 5. If you were to ask me, hey, Candace, what's the most important chapter of the semester? It would be this chapter right here. This is a chapter that you want to get because there's so much left in the semester that is built on the back of this. I mean, yes, dimensional analysis is super important, but this chapter you really, really have to be able to understand. And the whole chapter is talking about molecules and compounds, how to write molecules, how to name molecules, how to read molecules, how to balance molecules. So when I say something like, hey, ammonium chloride, you'd be able to write a formula for it and you'd be able to tell me how many of each atom there are in it. If you can't do that, it gets really difficult later on in the semester to answer, let's say like a stoichiometry problem that says, hey, what is the mass of ammonium chloride in this problem? If you don't know even what ammonium chloride is, or, disulfur dioxide or whatever it happens to be, that's going to give you a lot of trouble. You're going to be sort of caught up on this chapter. In addition, as far as the final is concerned, I mean, the final ends up being like 50 multiple choice questions. And I think like 10 or 12 of the questions directly relate to this chapter. So we're talking, a fifth to almost a fourth of the test is like finalists sitting in this chapter. So definitely want to know how to do this. Okay. So sugar's properties. So sugar's properties differ from those of the elements C, H, and O, which are contained in sugar. So here is a little packet of sucrose, and here's what the molecule looks like. But It's made up of carbon, hydrogen, and oxygen. The properties of carbon, hydrogen, and oxygen vary a great deal from the sugar itself. You wouldn't want to be eating carbon on its own. That would be something like graphite or a diamond. But when it's mixed in certain proportions, you get this nice sweet thing that we can put in our tea. Same thing with sodium chloride, which is table salt. Sodium chloride is NaCl. It contains sodium. This is a piece of sodium right here. Sodium is a very reactive metal, and it dulls really quickly when it's exposed to air. It doesn't look very appetizing. Over here, I've got elemental chlorine, which is a yellow gas, and it has a really nasty odor. It's super reactive, and it's also poisonous. So both of these things seem unappetizing, right? But when we put them together, we get sodium chloride, which is table salt. The properties of a compound in general will be different than the properties of the element that it's made up of. Sometimes there's overlying similarities, but a lot of times the compound will act totally different. So when I say something like, oh, I've got sodium, don't just take, oh, sodium is obviously, she's talking about this. If I would have to specifically say sodium chloride in order to be dealing with table salt. So when going through your everyday life, some of the substances that we encounter in everyday life are elements, but pretty rarely. Maybe you've got a gold ring that's made out of mostly gold, or a platinum ring. You might have a diamond that's made out of pure carbon, right? But in general, most of the elements that we are going to come into contact with are going to be presented as a compound. That's why knowing the names and being able to identify compounds is so important, because most of what we interact with are compounds. Free atoms, or atoms that are by themselves, are pretty rare in nature. Things like noble gases tend to be free elements. Sometimes we'll see some of the other things, metals, by themselves, but in general, things like to combine with other elements in order to create a more stable structure. It's important to note that a compound is different than a mixture. So if we go back to identifying matter, a compound has a definite fixed proportionality, like H2O would be an example of a compound, right? H2O. Two hydrogens need to literally be bonded to one oxygen. Another one, NaCl, one sodium is bonded to one chlorine. These are examples of compounds. A mixture would be salt, water. Okay, that's taking these two things and adding them together. I'm not fusing or bonding this to this. They're not sharing or transferring electrons. They're just simply occupying the same container. This is getting dissolved in this. So with a compound, the element combine in fixed definite proportions. So there's a specific recipe for a compound. With a mixture, you can have varying proportions. You could have a very salty water. You could have a water that's less salty. So compounds display constant composition. What that means is that whether you have a very small amount of water, like one molecule, or a whole water bottle, or a full water balloon of water, the composition or the proportionality between them will be the exact same. So if I have one molecule, my ratio of hydrogens to oxygens is a 2-to-1. If I have an entire bag full of it, my ratio of hydrogens to oxygens is still 2-to-1. A mixture, on the other hand, again, there are relative amounts. This is a mixture of hydrogen and oxygen. So it's the same stuff that's in the water balloon, but these guys aren't fused together, right? Here they're fused into their water packets, which gives them the properties of water. Here we've got hydrogens and oxygens floating around. Could I potentially pump more oxygen in here? Yeah, and change the proportions. That is not something that you can do with a compound. With a compound, if I put more water in, it's still going to have that ratio of 2:1. So Joseph Proust stated the law of constant composition, which says all samples of a given compound have the same proportions of their constituent elements. So again, all samples of a given compound, so this is talking about a compound, they have the same proportions of the constituent elements. So whether I have one H2O molecule, let's say I've got one H2O, or I've got 1 gram of H2O, or I've got 100 grams of H2O. In every one of these cases, my hydrogen to oxygen is going to be a 2:1 ratio. Doesn't change. So the mass ratio of elements in water, for instance, is always constant. If we were to decompose 18 grams of water, we would get 16 grams of oxygen and we would get 2 grams of hydrogen, or an oxygen to hydrogen mass ratio of 16:2 or 8/1. This ratio is different than the atom ratio. This is your mass ratio. Okay, my atom ratio for H2O would be 2 hydrogens for every 1 oxygen. My mass ratio is, this is 16 grams, this is 2 grams. It doesn't matter if the sample was 18 grams or 180 grams, you'd always end up with this ratio of 8:1. Any sample of pure water will have that ratio of 8:1. Another element, ammonia, which is NH3. If we were to decompose 17 grams of ammonia, we would get 14 grams of nitrogen and 3 grams of hydrogen, or there's a ratio of 4.7:1. So I'm not going to have you like memorize the mass ratios for every single compound that's out there, but just conceptually know that there is a mass ratio that stays consistent throughout, whether you have 1 gram of it or 100 grams or 1,000 or 1,000,000 grams. It's always going to be a consistent ratio for whatever that specific compound is. So how do we write a compound? Well, because compounds have a constant composition with respect to their mass and are composed of atoms that are also in fixed ratios, we get to write our chemical formulas or our chemical compounds using a chemical formula. So a chemical formula will tell you each element that's present in the compound. So we don't write elements we don't have. And then we write the relative number of atoms for each one. So it's sort of like your recipe for your compound. So the recipe for H2O is 2 hydrogens for every 1 oxygen. That is its chemical formula. That is what you need in order to make water. Our ratio would be a 2:1. The chemical formula contains, we always use the symbol of the element, so we don't write the whole name hydrogen out. We just write the symbol out. And then we will put a little, what's known as a subscript. So subscript means it's a number sitting slightly below. A superscript is a number that sits slightly above. So the subscripts are always telling you how many of the atom before you have. So in this case, the 2 is talking about my hydrogen, okay? If you only have 1 of the atoms, it's just inferred, right? I wouldn't write oxygen if I didn't have 1 of them at least. I don't just write random elements down and say, oh, I have 0 of them. So there is an inferred 1 here that's applying just to the oxygen. So just for our convenience, we can ditch the 1. So there is water, 2 hydrogens, 1 oxygen. So you want to start getting in the habit of being able to read these out. How many of these do I have? How many of these do I have? So chemical formulas, how to represent compounds. So here are some examples of some common chemical formulas. First one here is NaCl, which is table salt or sodium chloride. In this case, our ratio is 1 sodium for every 1 chlorine, or a 1-to-1 ratio. This thing over here, this is something that we exhale and plants take in, carbon dioxide, CO2. The ratio of carbon to oxygen in this case, 1 carbon for every 2 oxygens. There's a little bit more of a complicated formula. This is table sugar. Don't get scared and think, oh my gosh, she's going to make me memorize these formulas for table sugar. This is what's known as an organic compound. An organic compound is anything that contains carbon in it like that. That is a whole different set of naming and nomenclature and all different sorts of rules that we won't get into. If you take 130, which is the organic biochem class, you'll learn about organic chemistry. Or if you end up having to take specifically an organic chem class, you will get into how these things are named. So don't get scared by this, but this and this, by the end of this lecture, you should be able to name both of those. And as long as you have a periodic chart, you really have all the tools you need. Okay, so looking at this one, much bigger molecule, right? I've got a 12 to 22 to 11 ratio, or 12 carbon, 22 hydrogens, and 11 oxygens. That is the recipe to make table sugar. If just one of those oxygens happen to fall off, which they don't just fall off, you have to do something in order to remove one. But if one of them was to fall off and you now had 10, you would have a different formula. It would have different properties. It would no longer be sugar. And then the subscripts in a chemical formula represent the relative numbers of each type of atom in the chemical formula. Yeah, so we've already sort of talked about that. So this is a perfect example of why it is so important to make sure you're using the correct subscripts. Sometimes, especially later on when we start balancing things, people will say, well, I don't need 2 oxygens. I just need 1 oxygen. So instead of writing CO2, I'm just going to write like CO, because I mean, they're both carbon and oxygen, right? No, those are not the same thing. Okay, this is carbon monoxide, carbon with 1 oxygen. This is carbon dioxide, carbon with 2 oxygens. How are they different? Carbon monoxide is a pollutant that has really adverse health effects for humans. It's not something you want to breathe in on a regular basis. CO2, on the other hand, is a relatively harmless gas that we breathe out, and we breathe in like throughout the day. Now, you don't want to be locked in a room with only CO2 because you will pass out and won't come back. But totally different things, okay? And all that I'm changing is that little subscript. So very important. You can see structurally here, we've got the carbon with 1 oxygen. Here we've got the carbon with 2 oxygens. So different properties. So don't go changing subscripts on me. You have to make sure you're using the right subscripts. So when we're going to name something, you notice this, I call this sodium chloride as opposed to chlorine sodium. The reason is because we always list the more metal thing first. All right, so if we've got a metal and a non-metal, I'm going to write the metal first. Let's say that we have a compound that doesn't have any metals in it. So again, that's how do you know if it's a metal? Remember off of your periodic chart, okay? Your periodic chart, the things that are to the left of the zigzag are your metals. The things that are to the right, upper right-hand corner, those are your non-metals. So If you have two things that are non-metals or there isn't a metal in it, you will list the thing that's more metal-like first. How do I know something's more metal-like? It's closer to the zigzag line. So let's say we have nitrogen and oxygen. Let's find on our periodic chart nitrogen and oxygen. That's number 7 and number 8. Nitrogen is sitting closer to the zigzag line, so I'm going to say the nitrogen first or list it first, and then I'm going to put the oxygen afterwards. All right, another example is if we combine sulfur and oxygen. I'm going to list sulfur first and then oxygen because, again, sulfur is closer to the zigzag line. It really is that simple, okay? So metals to the left, nonmetals to the right. If you are two nonmetals, the thing closer to the zigzag you list first. Are there exceptions to that rule? Obviously, there's always exceptions. One of those exceptions is this thing right here. This is a polyatomic ion, which we'll talk about in a little bit. OH, or the hydroxide ion, OH minus, we list oxygen first. It's just how it is. All right. So this is sort of the general ordering of the nonmetals in their order. So first carbon, then phosphorus, then nitrogen, then hydrogen, then sulfur, iodine, bromine, chlorine, oxygen, and fluorine. Again, it sort of follows that zigzag. You should be okay with, if it's closer to the zigzag line, list it first. If you want to memorize this chart or have access to it, you can, but you should be okay with just that. Okay, so we're gonna come back to this because I don't know why it does this. And I guess we can talk about it. So some chemical formulas contain a group of atoms that are acting as a unit, or think of it as a packet. These are known as polyatomic ions. So that name sounds scarier than it actually is. Polyatomic ion. So what does poly mean? Poly means many, like polygamist or polytheist, right? Multiple wives, multiple gods. So this is multi or many. Atomic is atom. Atom. And then ion, we remember from our last chapter, is just a charge, right? It has a charge. So it's multiple atoms with an overall charge. So I'll give you an example of a polyatomic ion, OH minus. This is hydroxide. We have oxygen and hydrogen, and they are, when they're combined together, they have an overall -1 charge. Another one, sulfate, SO4, 2-. In this case, I've got 1 sulfur combined with 4 oxygens. This packet has an overall 2- charge. Remember, the charge is your superscript in the upper right-hand corner. Okay, that charge applies to the entire polyatomic ion. So when writing chemical formulas, when you have a polyatomic ion, let's go ahead and add up some of them. So this is something called magnesium nitrate. So when looking at this formula, if I was to add everything up, okay, the easy thing is to see that I have 1 magnesium, right? So we got 1 magnesium. Now what we see is that we've got this nitrate ion, but it's set in parentheses, which means that I've actually got 2 of these nitrate ions. So if I've got nitrate, which is nitrogen with 3 oxygens, and I multiply it by 2, that means I really have 2 of these guys. So the 2 gets distributed to both things within the parentheses. So in this case, I'll have 2 nitrogens, and then my oxygen, I have 3 oxygens inside. I have to multiply it by the 2 to give me a total of 6. Or I can look here, if I've got 2 of these little packets, 1, 2, 3, 4, 5, and 6. All right, so when looking at this, again, the metals listed first, then it lists the nonmetals or the polyatomic ion. The 3 subscript is talking just about the oxygen. The 2 subscript is talking about the entire polyatomic ion. So get in the habit when you see parentheses, it's a polyatomic ion in there, you need to multiply it out by something. We're going to come back to these polyatomic ions a little later, so you'll feel a little bit more comfortable with them. There'll be certain polyatomic ions that you're going to want to have readily available. One thing you can do is print off a polyatomic ion chart. You go on Google and type in polyatomic ion chart, you'll be able to find all the polyatomic ions that you would need for this class. There's also one in your textbook as well. Okay. So there's a couple different types of chemical formulas. One is known as an empirical formula. An empirical formula gives the relative number of atoms of each element in a compound. So this is saying, hey, I've got a 1-to-1 ratio, or I've got a 2-to-2 or a 2-to-4 ratio, or no, not 2-to-4, 2-to-5 ratio. So HO would be an example of an empirical formula. It's 1 hydrogen for every 1 oxygen. Now the molecular formula is what's actually happening in the atoms within the molecule. So in that case, the molecular formula is always going to be some sort of multiplier of the empirical formula. So H2O2 would be an example of a molecular formula. I've got 2 hydrogens for every 2 oxygen. This is what's actually happening in real life. If I was to reduce this down, I would get to my empirical formula. Because again, the empirical formula is really just a relative relationship. This tends to come into play more when we're dealing with nonmetals. When we deal with a metal and a nonmetal, it's already reduced for us. So the molecular formula is always a whole number multiplier of the empirical formula. So I'm going to give you a molecular formula, and I want you to tell me what the empirical formula for it would be. All right. So let's say we've got C11H22O33. That's the molecular formula. I want you to write an empirical formula for this. So that's the lowest possible ratio of those 3 things. Okay, so if this is our molecular formula, this is some sort of multiplier of our empirical formula. In this case, I can see that I've got 11, 22, and 33. All of those are multiples of 11. So if I divide each of these by 11, I can get to the base ratio, which is 1 carbon for every 2 hydrogens and every 3 oxygens. We would say that this is the empirical relationship or the relative relationship. This would be the molecular. And we'll talk more about that in chapter 6, like down the road some. We're not doing chapter 6 right after this, just FYI. Okay, we can also do represent a chemical formula using what's known as a structural formula. In this case, we use lines to represent chemical bonds, and we show kind of relatively where the atoms are in space. So the next page should show us that. Here we go. So here I've got methane. This would be its molecular formula. And then I've got a structural formula. So instead of just writing out what I have, I'm actually going to draw it sort of. So I've got carbon in the center, and then the 4 hydrogens sit around the carbon, each hydrogen being attached to the carbon. None of the hydrogens are bonded to each other. They're just all bonded to the carbon. Sometimes we can draw it as like a ball and stick model. This gives us sort of a 3-dimensional shape. So we've got a tetrahedral here, carbon in the center, and then this sort of little pyramid shape. Or sometimes they do it as a space filling model. All these things are talking about the same formula. They just sort of give us more information as we go along. Obviously, these become more cumbersome to draw or write. So the more chemistry you do, the more you should start to be able to look at something like this and visualize something like this or this. Don't expect you to be there right now, but with time. So we don't need to talk about that. Okay, so let's talk about a molecular view of elements and compounds. So pure substances, if we talk about matter, matter can be represented as either a pure substance or a mixture. We're going to hang out in the pure substance part. So pure substances can be either elements or compounds. In order for it to be a pure substance, it needs to have like a consistent composition. If it's an element, it's made up of one type of atom. If it's a compound, it's made up of more than one type of atom. Elements can be either atomic or molecular, and compounds can be either molecular or ionic. So visually, all of this is displayed over here. All right, so we've got our pure substances, and we're going to break it up into either elements, it's one type of thing, compounds, it's more than one type of thing. If it's an element, it can be what's known as atomic or molecular. And if it's an element, it can be atomic or molecular. If it's a compound, so if it's made of two or more things, it can be either molecular or it can be ionic. These are just going to drive me crazy. So let's go into each of these. We'll talk about elements first since they're simpler. So an element is made up of one type of material, like aluminum or oxygen or gold or silver. In an atomic element, so in this section right here in the first part of this, atomic elements are those that exist in nature with single atoms as their basic unit. Most of the elements on the periodic chart are in this form. All right, so if I have something like titanium, its smallest basic unit is just going to be one titanium atom. Now, molecular elements are a little bit different. Sometimes these are called diatomic molecules. You can see it down here, diatomic. Don't get freaked out by that. Di just meaning two, okay? So with molecular elements, the base unit for these are going to be two atoms paired together. They don't like to exist on their own. They're more stable when they're bonded to themselves. So an example of a diatomic molecule would be this thing over here, chlorine. Chlorine likes to bond with itself. So when we find it in elemental chlorine form, we're going to see it as Cl2. An atomic element would be mercury. Mercury is just a single set of mercury atoms. So you do need to know, you do need to have all the diatomic molecules memorized. Here they are. So I would recommend if you've got your periodic chart, just highlight them or color them in right now. You start off with hydrogen in the upper left-hand corner, okay? Then drop down over to nitrogen. And then you just move over and down. So it's going to be nitrogen, oxygen, fluorine. Then go down chlorine, bromine, and iodine. So you make sort of an upside down L. Okay, so hydrogen, and then we've got these guys here and these guys down here. Those guys exist as diatomic molecules when they're by themselves. One way to remember, have no fear of ice cold beer. The cold is not carbon, it's chlorine, and beer is not boron, it's bromine. So everything else forms just an elemental or atomic element, okay? So just these guys form the diatomics. So highlight them, circle them, mark them, do something on your periodic chart so that you can reference that pretty easily during exams and homework. All right. So if we go over to the compound section, we can define a compound as being either molecular or ionic. A molecular compound are compounds formed when two or more nonmetals share electrons. So in this case, we have a shared electron. The basic unit of a molecular compound is a molecule composed up of its constituent elements. An ionic compound contains one or more cations. A cation is just a fancy way of saying a charged positive particle or a metal. So in a ionic compound, most of the time, it's a metal combined with a nonmetal. This seems really simple, but it always seems to trip people up, and it's just so important to be able to identify the difference between these two, okay? An ionic compound has a metal combined with some sort of nonmetal or polyatomic ion. A molecular compound is two nonmetals. Why do I need to know the difference between these? Because the way that I name, identify, and write formulas for this is completely different than the way I do it for molecular. So because of that, we're going to actually practice some of these. So I'm going to write down a couple chemical formulas for you all. And I want you to tell me, right now, all I want you to do is tell me, is it a compound? Well, they'll all be compounds. I want you to tell me if it's ionic or if it's molecular. Okay, all I want you to do right now, you don't need to name them. I just want you to tell me, is it molecular or is it ionic? Give you one more minute. Okay. So we're just deciding if these are ionic or molecular. So looking at this, I've got carbon mixed with oxygen. Both of these things are nonmetals. How do I know that? Because I'm looking at my periodic chart and I'm seeing that they're both to the right of the zigzag line. If I have two nonmetals, two or more nonmetals, we're going to say it's molecular. Okay, so then we will use the rules for molecular to name it. This thing here, I've got Mg and O. Mg is number 12, that's a metal. O is our nonmetal. So this is combining a metal and a nonmetal. This thing is going to be ionic. I want this to feel super, super, super simple. This whole chapter, we're going to kind of just go real slow through it so that we can make it feel really easy. Sulfur and oxygen. Okay, looking at my periodic chart, sulfur is 16, oxygen sits right above it, 8. Both of those are nonmetals, so this is going to be molecular. This next one here looks a little bit scarier, but let's just break it down. I've got Al and then SO4. This is a polyatomic ion. Again, we'll get into polyatomic ions a little bit more later. This thing here, this is aluminum, right? Aluminum is a metal. If I've got a metal in there, it's going to be ionic. This last one here, Cl and F. Okay, chlorine is 17, fluorine is 9. Both of those are nonmetals. This is going to be molecular. If you have any questions on these, please ask. You can turn your mic off real quick and just ask me a question because I want to make sure that we got this. Because if you can't, or you can throw it in the chat if you want to, because if we can't identify the difference between those, it's going to throw us off for the rest of the chapter.
So as long as the compound has a metal in it, it's
Yeah, for the sake of this class, if you're seeing a metal as that first thing written, you can say it's ionic.
okay, but it has to be first, or
yeah, it has to be written first. Sometimes metals can get inserted into other areas. But for the sake of this class, since we're not doing organics and stuff, yeah, if you see that metal popping up as the first thing written, you're going to be ionic.
Okay.
Okay. Cool. Any other questions there?
Does it matter how many numbers are on the bottom, or is it just the metal and the non-metal?
For this point right now, we're not talking about the numbers. Yeah, those numbers are important, obviously, and they will come into play later on. But for right now, as far as just being able to identify, oh, I don't know what that did. Being able to identify molecular or ionic, it only has to do if it's a metal and a non-metal or two or more non-metals. Okay, that's all we're doing at this point.
Thank you.
Now you may see something like this. HCl, okay. H is definitely a nonmetal. Cl is also a nonmetal, but this is one exception. This is it's two nonmetals, but anytime you have hydrogen written first like this would be classified as an acid. Okay. So if you ever come across a compound where the H is sitting in the front, it is an acid, something like this, HNO3. That H in the front makes this an acid. We will name it in a different way than we do our molecular things. Okay. We'll come back to these a little bit later on. So up top here, I've got CO2. Now the base unit for a molecular compound, one way to remember it, molecular, the base unit is a molecule. So the smallest identifiable thing within this is going to be one little molecule or little sort of bubble packet of CO2. That is different than what's happening in an ionic compound or when we have a metal and a non-metal. The base unit that composes table salt is NaCl, but this is known as a formula unit as opposed to a molecule. And here, they're little packets of CO2 that are smushed together. In this case, I've got sodium chloride, but it's in this three-dimensional matrix. So every sodium is sort of slightly bonded to all the chlorines around it, and vice versa. Every chlorine has multiple sodium sort of buddies. It creates this lattice structure. So let's go into ionic stuff first. So ionic means we've got a metal combined with some sort of nonmetal. Well, in an ionic compound, when a metal, which has a tendency to lose electrons, remember metals like to form cations, which is just a fancy way of saying that it forms a positive charge, combines with a nonmetal, which likes to form an anion or forms a negative charge because it gains electrons. What will happen is one or more of the electrons will transfer from the metal. So this guy loses the electron and this guy sucks the electron up. Now what happens then if this thing loses an electron and this gains an electron, this gets a positive charge, this gets a negative charge. What happens with positives and negatives? Opposites attract, so they will stick together. All right, so that difference in charge is sort of acting as the glue of our ionic compounds. Just to hit it home, a compound composed of a metal and a nonmetal is considered ionic. The base unit is a formula unit. Unlike molecular compounds, ionic compounds do not contain individual molecules, but they create this cation, anion lattice work in 3 dimensions. So if we're going to write a formula for ionic compounds, the first thing we want to do is review the charges. Oops, sorry, we want to review the elements that form predictable charges. So grab your periodic chart. Remember, above column 1, what did I have you guys write? I told you to write a +1 or a +1 charge. If you didn't, do that now. Okay, over column 2, a +2 charge. Column 3, so I want you to hop over the transition metals, hop over the middle guys, go to where boron is. This isn't including boron though, okay? So aluminum 13 and gallium 31, those guys, we're gonna put a +3 charge. Skip over carbon and silicon, go to the 5th column, which is where nitrogen and phosphorus is. Above that, put a 3-. Above oxygen and sulfur, put a 2-. Above fluorine, chlorine, bromine, iodine, put a 1-. And then above the noble gases, that very last column where helium, neon, argon, put a 0 or a 0 with a slash through it, just to let you know that those don't usually form charges. The other thing I want you to fill in, so we had aluminum, go back to aluminum, which is 13, which is a 3+. Go in a zigzag down to the left. So aluminum is a 3+, go to zinc, which is 30, that's a 2+, and then go to silver, number 47, that's a 1+. So it should be aluminum 3+, zinc 2+, silver 1+, 3, 2, 1. Zinc and silver are sitting in the transition metal area, but they have a predictable charge. Okay. So we'll treat them like the predictable guys. So now that we've got those down, what about the transition metals? Those can have multiple charges, like iron could have a 2+ or it could have a 3+ charge. You'll always be able to figure out which charge you're working with. We'll get into that later. Let's do the easier ones first. So in an ionic compound, it will always contain 1 positive and 1 negative ion, or the metal and the nonmetal, or the polyatomic ion. In a chemical formula, the sum of the charges of the positive ion, the cation, always must equal the sum of the charges of the negative anions. So your positive charge and your negative charge have to sum up or equal each other so they can cancel out, because the overall formula has to have a 0 charge. So let's see. Exactly, like MgO. So that's why it's written as MgO as opposed to Mg2O, right? Or Mg5O. Why is it always consistently MgO? Because that's what's giving it the charge balance. Now you can conceptually think when you look at MgO, well, magnesium has a 2+ charge, right? And oxygen has a 2- charge. So one of them would balance the other one out. It gets a little trickier when you've got something that's got a 1+ and something that's got a 3+ or a 2 and a 3 or whatever. So there's a really quick way to figure this out. This is how you're going to do it. So you write the symbol for the metal and its charge, followed by the symbol for the nonmetal and its charge. I'm going to do that on the board over here. So let's say we're going to combine calcium and fluorine. So according to our steps, the first thing we do is we write a formula. Don't smush them together yet. Write the name as a symbol and put its charge. So calcium is always in the second column. It always has a 2+ charge. Fluorine is in the 7th column. I'm going to write its symbol with its charge, which is minus. You can put -1 if you want to, or just minus. Okay, that's the first step. Next thing we want to do, this is going to sound weird, but make the magnitude of the charge on each ion without the sign. So remove the sign, just take the number and let that become the subscript of the other ion. If possible, reduce the subscripts to give a ratio with the smallest whole numbers. Check to make sure that the sums of the cations are exactly equal to the sums of the anions. So that whole step about the magnitude thing. So what I'm going to do is take this number here. I'm going to ignore the charge. This is going to become the subscript of the other guy. So this charge is going to let me know that I have 2 fluorines. Over here, this is a 1. I'm going to erase this. This tells me I have 1 calcium. So calcium is 1, fluorine is 2. This number gets dropped down there. This number gets dropped down there. That's the fastest way to get charge neutral. So my symbol for calcium and fluorine would be CaF2. I can go back and check and make sure that it is in fact charge neutral. What's the charge on calcium always? It's always 2+. 2+. And how many of them do I have? In this case, I have 1, right? Fluorine always has a -1 charge. And how many of them do I have? 2. All right, so this is a 2+ and a 2-. When I add those things together, what do I get? 0. They've charge neutral. Let's look at what they have here. So they took aluminum and oxygen. So aluminum always has a 3+ charge because you've found that on your periodic chart, right? There's our aluminum at 13, 3+. Oxygen always has a 2-. Some of these charges are going to start to you're going to memorize them. So oxygen has a 2-. So what we do is we take the magnitude of the aluminum's charge and we drop it down to the oxygen. We take the magnitude of the oxygen's charge and we drop it down to the aluminum. The formula for aluminum and oxygen will always be Al2O3. There isn't another possibility, at least not for this class. So last step in the beginning, at least, is to go back and check. So aluminum, we said, has a 3+ charge, right? And I have 2 of them. Oxygen has a 2- charge, and I have 3 of them. So this is 6+, this is 6-, 0. For this one over here, magnesium and oxygen, we've got Mg 2 and 2, so they get it to Mg2O2, but anytime it's ionic, this is not true for molecular, this is only true for ionic, you can reduce those down so that it becomes MgO. All right, we're going to do some examples, but any questions just yet before I give you guys a bunch of examples to work on? Anything that you're not liking or is not making sense, or why? Why do we flip-flop? Because that gives us the our like even multiplier. You could technically go and say, okay, well, aluminum's got a 3+ and oxygen's got a 2, so I'd need 2 of these for every 3 of these to give me 6. You can do it that way, or you can just flip-flop. It's the fastest way. So I'm going to give you a couple things. If you have a question, let me know. But I'm going to give you guys a couple things to do. Metals and nonmetals. I want you to write the correct formula. Okay, so we're going to combine lithium and sulfur. Strontium and nitrogen. Zinc and phosphorus. And one more, iron and bromine. Okay, so I want you to write the correct chemical formula for each of these things. I'll give you, let's see, it's 8:58. I'll give you guys till 9:05, so 7 minutes. Okay. So looking at these guys, the first one, we've got lithium and sulfur. The first thing I want us to do is write out the symbol for each with its charge. Lithium always has a plus charge. Sulfur always has a 2- charge. I'm not making these things up. I'm just looking at my periodic chart. So you don't have to pull these things out of thin air as long as you've got your periodic chart with you. So then we're going to take the magnitude of each. So this has a magnitude of 1. This has a magnitude of 2, and we're going to flip-flop. So lithium should be a subscript of 2, and sulfur should be a subscript of 1. So I need 2 lithiums to balance out every 1 sulfur. Any questions on that one? If you have, at any point, if you're wondering, where are you getting these numbers from, ask me. Okay, strontium, SR, its charge is always a 2+. Nitrogen is always a 3-. Flip, flop. Strontium should have a 3 at the bottom. Nitrogen should have a 2 at the bottom. This is the only way to correctly write strontium nitride. This is the only correct way to write lithium sulfide. Zinc and phosphorus. Zinc is one of those transition metals that has a predictable charge. So zinc always has a 2+. Phosphorus, P, always has a 3-. Flip flop, Zn3P2. Similar ratio to the one above it, right? Okay, last one here. This one was to throw you off. So iron and bromine. So we go to write iron and we go, what is its charge? We don't know. We don't know what its charge is. Bromine, I do know. Bromine has a minus charge. I don't know what this charge is. This is a question mark right now. So the way that this is written is saying iron and bromine, there's not enough information there for you to write a correct formula. We will come back to ways to write this. But right now, this thing doesn't have enough information for you. So just 3 of those. If I was to write something like this, carbon and oxygen. Carbon, is it a metal or a non-metal? It's a non-metal. Oxygen, is it a metal or a non-metal? It's a non-metal. So we do not flip-flop charges. Don't balance charges for molecular. Don't do it. All right, we only get to use that when it's a metal and a non-metal. Okay, I'm going to pull the slides back up. See what else we got going on in here. We can get through one more little thing. Okay, here's a list of polyatomic ions. So traditionally in class, I would have you guys memorize some of the polyatomic ions, but because of the nature of the semester, you guys will get to be able to use a reference for these. So the ones that we tend to see quite often, or I use a lot, are acetate, carbonate, bicarbonate, hydroxide, nitrate, nitrite, phosphate, ammonium, sulfate, sulfite, maybe cyanide. Those tend to be the ones we use a lot. So each of them has a given name, and then it has a specific formula with its charge. The thing with polyatomic ions is the charge is just as important as knowing how many of each atom you have. So make sure when you have carbonate, you're not just like sloppily writing, oh, isn't it like CO3? No, it is CO3 with a 2- charge. That is super important to add that charge, because that charge helps us to balance out metals and nonmetals. So let's balance out some things with a polyatomic ion, all right? Yeah, we've got 5 minutes left. I'll give you 2. Well, we'll do one together and then I'll give you one. So the first one I'm gonna do is, let's combine, I'm gonna combine magnesium with sulfate. Start to get in the habit now. If you see something ending with ATE or ITE, those are polyatomic ions. So if I'm saying sulfate, I'm not talking about sulfur. I'm talking about sulfur combined with 4 oxygens that has an overall 2- charge. So in this case, magnesium sulfate. So magnesium is Mg. It's got a 2+ charge. Sulfate is SO4 with a 2- charge. Now, what I tend to teach people in this is to circle the atoms with the polyatomic ion. So circle this so that we can start thinking about it as a packet or a unit. So this 2 is going to get dropped down to my sulfate, and this 2 is going to get dropped down to my magnesium. So magnesium will have a 2, sulfate, I'm going to put it in parentheses, it'll have a 2. Now this can be reduced down to MgSO4. Do one more together. Let's combine something that doesn't cancel. I'm gonna do calcium and nitrate. Okay. So calcium, Ca always has a 2+ charge. Nitrate is a polyatomic ion. You see that ending of ATE or ITE, you're going to go to your polyatomic ion list. So nitrate is specifically NO3 with an overall minus charge. I'm going to circle this so I can keep it as a unit or a packet. So this 2 is telling me how many nitrates I should have. So I should have 2 nitrates. The 1 here is telling me I should have 1 calcium. So Ca, I'm going to put it in parentheses, NO3 with a 2 charge. This thing needs to be put in parentheses. Your polyatomic ion needs to be put in parentheses if you have more than one of them. If you have just one, like in this case, you just write it. If you have more than one, it needs to be in parentheses. What I see happen a lot is this. Someone will flip-flop. Okay, what I'm writing right now, these are the wrong things. This is the wrong way to do it. So if you're writing it down, write it in red pen. But what I'll see people do is they'll go, okay, I've got calcium, I've got one of those, and nitrate becomes NO, and they take the 3, and for some reason, they put the 2 in that place. That is not calcium nitrate. That is actually calcium nitrite. That's something different. You don't want to change subscripts. It changes what it is. So this, wrong. Another thing I see people do is they'll flip-flop and they'll say calcium, okay, and I'm combining it with nitrate, NO3, 2, and not put the parentheses in there. Why is that wrong? Well, this is telling me that you've got a calcium, a nitrogen, and 32 oxygens. You need to put the parentheses around there in order for it to be multiplied correctly. All right, we're going to stop there. Any questions on that? Any quick questions that you want to throw out there? You can just unmute and say, why do we do that? Or where's that number coming from? Or you can put it in the comments. Otherwise, you are all free to go. Make sure you take your test. Don't forget to take your test. Take it by midnight. And I will see you on Wednesday. If you have any specific questions that you want to hang around for, please stay and I will put you in a waiting room. Otherwise, have a good rest of your chilly Monday. Bye, guys. Suzanne? Looks like it's just you and me if you got a question.